Welcome to lecture 7 of module 4. We have been discussing in this module about the convective heat transfer correlations, and in previous few lectures we have discussed how to get the values of heat transfer coefficients through the use of different correlations available for different geometries and different conditions. Now, today's lecture, which is also related to convective heat transfer coefficient, here we are going to discuss some important aspect which is also called as momentum and heat transfer analogies. So, just to start with that the chemical engineers do study the momentum transport while we will study the course fluid mechanics. There the momentum transport is discussed in detail, and in this course we are discussing about the heat transfer part. Now, there is a link between these two things. There are some similarities, some basic laws of transport of momentum and heat transfer can be expressed in the similar form, in the similar manner, and therefore, there is an existence of some analogies. Okay. So, we are going to see that how heat transfer and momentum transport will be analogous to each other, and what is the advantage or benefit of having such analogies. Okay. Now, if we just consider a case to understand in detail about these particular things, we consider a pipe flow like this. So, this is the pipe, and this is the center line. Okay. And here we know that when there will be a flow, so flow is in this direction, say, and this is the there will be a laminar sublayer here in this zone. So, these are related to fluid mechanics. Even after that we should understand, and say we know that there will be a velocity profile in this pipe zone when there will be a velocity profile, and so V z, if I say that this is the z direction. Okay. So, we will say that this is r, this is z, and this is r, and so V z is a function of r, that we know, and therefore, the velocity profile that comes into picture. And what happens is that this is the laminar sublayer and this portion is the turbulent core. That means that some in this region there will be a laminar flow, and then in this region there will be some turbulent flow that will occur. And what is happening, when there is a flow and there is, say, wall, this is the wall of the tube or pipe, this is T w, say, and T w is always greater than T. So, in here in this you can have, say, temperature profile also, and we will say that this is a function of r. So, always we will have T w is greater than T or as a function of r, and T w is the wall temperature which is maintained constant. So, what happens, this is a constant temperature. So, what happens, that heat is transported from the wall to the fluid. So, we can see that heat transport from wall to the fluid. Okay. So, in that case, if we say that the temperature gradient across this is this. So, if we say that dt by dr is the temperature gradient along r direction. So, while if we increase r, temperature will be positive. So, dt is positive. So, it is a positive quantity. And if we consider the momentum transport, what is the momentum transport? Momentum transport is nothing but that we know that when there is a flow through a pipe, that flow at the center line is the maximum velocity, and so momentum at the center line is maximum, and momentum of the fluid particles, fluid elements which is associated attached to the surface of the tube is 0, because there is no slip conditions. So, the fluid elements are attached to the surface, adhered to the surface, they have no slip condition, and according to the no slip condition they do not have velocity, or then once they do not have velocity they do not have any momentum. So, therefore, what is happening, the momentum is gradually, and we know that as we see the layers, okay, that here that from this also we can see that these are the velocities, okay, the velocity is gradually decreasing. So, momentum is gradually decreasing, but what is happening, momentum is transported along this direction. So, this is the direction of momentum transport and this is the direction of heat transport. Okay. So, if I say momentum transport direction, and this becomes heat transport direction. Okay. So, therefore, what happens is momentum transport is from center of fluid towards fluid layer towards wall, center of tube, wall of the pipe. And therefore, if we see and we understand that transport of energy that takes place, that on the in the very beginning we have seen is due to because of temperature difference. So, temperature difference is the driving force, and therefore, dt by dr is the gradient that is of importance to us, and we find that this driving force along r direction is positive. But here what is happening, the driving force for the momentum transport is velocity difference. So, if we see that dvz, okay, by dr is a negative along. So, it is along positive r direction, the velocity is decreasing. So, dvz by dr is negative, and so basically it is in the opposite direction the transport is taking place. So, this science indicates that. Now, in case of laminar flow or when there is a molecular transport, of momentum, molecular transport of momentum means it is in the molecule, transport is taking place by the molecules, and this happens when there is a little mixing in the molecules, when the molecules can behave individualistic and happens to be in the laminar flow region. Okay. So, when there is a molecular transport of momentum, then we know the Newton's law of viscosity is applicable. So, according to Newton's law of viscosity that we must see in the fluid mechanics books, okay, tau r z. So, tau r z means z directional momentum is transported along r direction. This z gives the z directional momentum, it is r means it is transported along r direction, that is what is this tau r z says. So, this is z directional, sorry, momentum is transported, okay, along r direction, and we know that this is given by minus mu into dvz by dr. We will assume that vz is function of r only, okay, and so we will say that vz is equal to function of r only, and this negative sign indicates that already we have decided that it will be z direction along r direction. So, this dvz by dz is negative we said. So, this negative and this negative makes it a positive quantity. Okay. So, that is why this also can be written as minus nu into ddr of rho into vz. Okay. So, this is nu is equal to mu by rho, which is called momentum diffusivity sorry. Okay. And we can find out that this is also this tau r z also can be told as momentum flux So, momentum flux is equal to momentum diffusivity into concentration of gradient of concentration of momentum. So, rho Vz is the concentration of momentum, and this concentration of momentum is nothing but rho Vz. This is nothing but momentum per unit volume, okay? Because we know that rho is equal to mass per unit volume. So, mass into velocity is nothing but momentum. So, momentum per unit volume, that is nothing but concentration. It is nothing but momentum per unit volume. Okay. Now, what happens is, in the similar way, if we see that we have already seen previously that heat transfer case, if we see that heat transfer, so heat flux also should be equal to thermal diffusivity into gradient of concentration of heat energy. So, that already we have seen previously. Even after that, if we just try to see this, it is given by Fourier's law, because in the, as I told, this the molecular diffusion is important. So, its conduction is very important things. Okay. So, then what is, and that happens in the laminar sublayer. So, laminar sublayer takes care of the conduction part. It takes place in laminar sublayer or any laminar region. In this case, it is the laminar sublayer. Okay. Now, what happens is, we can say that Q is equal to heat transfer rate. So, Q dot by area. Okay. If I say that this is the Q dot, heat transfer flux, this is equal to we know that K into dt by dr, where K is thermal conductivity. So, this is nothing but alpha into d rho Cpt by dr. That is what is happening. So, this is thermal diffusivity alpha, which is equal to K by rho into Cp, and rho is the density and Cp is the heat capacity of the fluid, and rho Cpt is the energy concentration, heat energy per unit volume. Also, it is called energy concentration. Okay. So, thus we can see that for heat transfer and for momentum transport, we can use the similar kind of relationships to express the heat flux and momentum flux. Now, when a flow is not only laminar, or when the flow is taking place by, say, there are some presence of eddy. So, when there is a turbulence, which is the most of the time we usually come across this kind of situations, then we say that this momentum or heat is being transported by eddies. So, this is called eddy transport. Eddy transport of momentum and heat takes place. So, therefore, we know in case of turbulent the flow situation that it is relatively difficult to predict, because the eddies means it is a chunk of molecules together moving together. Now, the sizes of the eddy can be varying, because depending upon the kind of turbulence and the molecular cohesiveness and many other issues, that eddies sizes can be different, and therefore, that mechanism of transport by the eddies may be defined. However, for a simplification of this, eddies can be viewed as like a single molecule. Okay? So, when we have a molecular diffusivity for heat, when we have molecular diffusivity for momentum, similarly we can have eddy diffusivity for heat and eddy diffusivity for momentum. So, therefore, if we write that epsilon h and epsilon m, so these are all eddy diffusivities for heat, energy and momentum respectively. Okay. Now, under this situation, what happens is we can redo or rewrite that transport equations, that basic form of the transport equation. So, Reynolds transport equation, Newton's law of cooling, if we try to write in a modified form. So, we can write that tau will be equal to minus nu plus epsilon m. So, we are taking care of both eddy diffusivity and molecular diffusivities together. So, contribution of both the things have been taken into consideration and into ddr of rho Vz. So, this is just to take care of a flow situation when both turbulence and initially laminar flow and then turbulent flow, and then when there is a turbulent flow, there is some contribution of the molecular diffusion also is there. So, therefore, contribution of both molecular diffusion and eddy diffusion has been taken into consideration for momentum transport. But in realistic situations, what we see or what we know that when there is a high flow or high level of turbulence, then molecular diffusion component is becoming negligible with respect to the eddy diffusion component. Okay. However, if we generalize like this way, then what we can write again for q dot also we can write as alpha plus epsilon h into ddr of rho Cpt. So, now if we try to see at the wall condition or at the wall, we can write that tau w will be equal to minus nu plus epsilon m into ddr of rho Vz at r is equal to capital R, and this is given as half into f into rho v bar square in general. So, v bar here it is called, f is called friction factor and it is called Fanning's friction factor. Rho is the density of fluid and v bar is called average velocity. So, this is as per the definition of the friction factor. Friction factor is defined as the wall shear divided by the inertial force. Wall shear force divided by the inertial force is nothing but the definition of the friction factor. So, F is defined as shear force by inertial force. So, this is called friction factor. So, based on that it is written, and then what we can write as between these two we can write that d v cap by say Vz cap, I say Vz, okay, by dr minus at r is equal to r equals to tau w by rho Vz bar into nu plus epsilon m. Okay. And this also can be written as a Vz bar by putting the values of tau w is equal to half of this, we will get as 2 into nu plus epsilon m. Okay. So, this happens and Vz bar is a dimensionless velocity. So, Vz cap here is nothing but Vz any v velocity at any point r divided by Vz bar. This is the average velocity along z direction. Okay. So, this is what is this gives the minus d v z by dr, this v z cap by dr at r equal to r is nothing but the velocity gradient of the dimensionless velocity, gradient of the dimensionless velocity at the wall, and this can be written like this, a v z bar by 2 into nu plus epsilon m. Similarly, in case of heat transport also we can write for heat transfer, we can write that alpha plus epsilon h into d dr of rho Cp into T at r is equal to wall will be equal to q dot w, that is the wall heat flux, and this we will write as h into T w, that wall temperature minus say T average fluid temperature. So, T average is the average fluid temperature. Okay. And thus, what we get is that dt, and now if we make it dimensionless again like previous one, at r is equal to r will be equal to h by rho Cp into alpha plus epsilon h, and then here T cap is written as T by T w minus T average. Thus, what happens is if we see between these two relationships. So, if I just tell this is say equation 1, and if I say this is say equation 2, between equation 1 and 2 some assumptions, Reynolds assumptions. Reynolds assumption says that gradients, number 1, gradients, I am sorry, gradients of the dimensionless parameters, okay, at the wall are equal, because that means the idea is as because it's being done by the molecules, it's a molecular level or transport that is being taking place at the wall. So, they are saying that that the gradient, so they are following the similar gradient for heat transfer as well as mass transfer. So, gradient of temperature, dimensionless temperature, gradient of dimensionless velocity, both will be assumed to be same. And the second case is that diffusivity terms also, because if the gradients are same, then maybe the diffusivity terms are also similar in nature, or so therefore, they are saying that diffusivity terms are like nu plus epsilon m should be equal to. This is a real assumption, it may not be exactly the correct thing that is happening in practice. So, these are the two assumptions that is being taken by Reynolds, and once we take incorporate these two assumptions in the equations 1 and 2, then what we get is from equations 1 and 2, okay, applying the assumptions, what we get that A v bar by 2 into I am sorry, it is will be getting h by rho Cp into V z bar, okay, and that is equal to f by 2. So, this is what is the simpler form, and this left hand side can be written as h d by k by simplifications into mu Cp by k into d V z bar rho by mu. We can understand that we are trying to write it in terms of some well known parameters. So, the first one is that is called Nusselt number. So, say Nusselt number based on the diameter of the tube, mu Cp k is the Prandtl number, and mu dV rho by mu is the Reynolds number through the pipe, and that is equal to F by 2, and this is also termed as Prandtl number based on the diameter of the pipe, and that is equal to F by 2. So, this part, so we say that Prandtl number is equal to F by 2. This is called a Reynolds analogy. As we understand that there are two assumptions being taken to discuss about this analogy. So, Prandtl number is equal to friction factor by 2, that is what is called Reynolds analogy. Many a times people uses that Darcy friction factor, this is I will denote as FD, and that is actually FD is 4 times the Fanning's friction factor, and therefore, many a times we may find the Prandtl based on diameter is written as FD by 8. Here this is also same thing, it is also a Reynolds analogy, where FD is equal to Darcy's friction factor, and the previous one is also a Reynolds analogy where F is Fanning's friction factor. So, we should be very careful to understand there are two types of friction factors are used in fluid mechanics. One is called Darcy's friction factor and is called Fanning's friction factor. Okay. So, different books, different places, they have used different notations, either somebody is using Fanning's friction factor, somebody is using Darcy's friction factor. Okay. So, this comes from the definition of the friction factor, how it is being defined. Okay. Now, second point here, I just wanted to say that we have seen that Prandtl number is equal to F by 2, and in Prandtl number we have Nusselt, Reynolds and Prandtl, and in that we have seen also that heat transfer coefficient term is there. So, idea behind this analogy is, if you see that we can write this Prandtl number like this. So, Prandtl based on diameter is H in by, as we have seen, rho Cp Vz bar. This if we write as H delta T by rho Cp Vz bar into delta T. What does it mean? It says that it is the heat transfer by convection okay, divided by heat transfer by bulk flow, heat transfer due to bulk flow. Okay. So, therefore, we can see that Prandtl number is the ratio of heat transfer by convection to heat transfer by due to bulk flow. So, as we find a Prandtl number for heat transfer like this, we may get a similar kind of number for mass transfer also, because there we can write that. So, we write that STD say M for mass transfer. So, here we will write for H for heat transfer. STD, this should be heat transfer, again sorry, here it will be not heat transfer, it will be mass transfer by convection divided by mass transfer due to bulk flow. So, what I just wanted to say is that as we have a friction factor versus heat transfer analogy or momentum transport versus heat transfer analogy, similarly we can have momentum transport versus mass transfer analogies also. Okay. Now, what therefore, we should write that the analogy should be that ST based on diameter here. So, I am not writing now based on diameter or whatever it is, depending upon the situations that ST can be defined. So, characteristic length. So, if I say this HTH for heat transfer and this is equal to F by 2, and STH for mass transfer, this is also F by 2, or STH is equal to say FD by 8, or STM is equal to FD by 8. Now, this is the Reynolds analogy for heat transfer and mass transfer, but our consideration is more restricted to mass heat transport situation. And now, what is the advantage of having this kind of analogies? Why we should have this? The advantage of having these kind of analogies are like what we find that there is a relationship between heat transfer. Basically, Stanton number is equal to F by 2. Say for heat transfer, Stanton heat is equal to F by 2. It gives me a relationship H versus F, friction factor relation. Now, what is there? Many a times it may be seen that correlations for H, heat transfer coefficient, may not be available for certain geometries, for which F value is available. So, then what we can do? Then analogy can get us the value of H. That is one important thing. Second point is performance or performing exhaustive experiments using heat transfer or using momentum transport. So, there is a trade off actually. In case of momentum transport or fluid mechanics experiment, it is relatively easier to perform the experiments, easier to perform momentum transport experiments and calculate the value of F. And many situations this performance of exhaustive. So, once we do this, then exhaustive conduction of experiments for heat transfer need not require. So, this will eliminate requirement of exhaustive and difficult heat transfer experiments. So, that is why that if we perform the fluid mechanics experiments, momentum transport experiments, calculate the values of F, and then from there we can get the values of heat transfer coefficient. That is what is the advantage that we can get from the analogies. So, similar is the case for mass transport. Okay. Now, the question is always the Reynolds analogy does not give a very high value, very good accuracy of estimations of heat transfer coefficient from fluid friction factor. So, therefore, there are some upgradation, there are some modification of this transport theorem. Now, the one important is that Chilton and Colburn suggested that the Stanton is equal to F by 2 by Prandtl to the power 2/3, or Stanton into Prandtl, I should write now H, Stanton heat transfer Prandtl to the power 2/3 is equal to F by 2. This is called, this is also an analogy, and this is equal to F d by 8. Okay. So, this is also an analogy, this is called Chilton-Colburn or Colburn, many times we will call it a Colburn analogy. So, according to them that this analogy performs better, than Reynolds analogy when Prandtl is not equal to 1. So, we can see when Prandtl equals to 1, this analogy it reduces to Reynolds analogy, but when Prandtl is not equal to 1, it performs better than the Reynolds analogy. Now, there is another analogy that is called von Karman analogy. Before that, we will see that there is an analogy that is called Prandtl analogy. So, what is being done in case of Prandtl analogy? It gives a little more realistic picture. Or mechanism of transport. It gives more realistic picture of mechanism of transport. Now, what happens is here it is assumed that the turbulent core it separately takes care of the turbulent core and the laminar sublayer near the wall. Okay? And therefore, it suggests that stanton is equal to f by 2 into 1 plus 5 root over f by 2 into Prandtl minus 1. Okay. Here, what is there in this Prandtl analogy is that in the turbulent core, the transfer is mainly in the turbulent core, the transfer is mainly by eddies. Okay. And in the similar sublayer, it is transport is through, and near the wall, that is laminar sublayer, the transfer is mainly, not mainly, transfer is by molecular diffusion, also called or diffusion transport, or we can say diffusive transport, normal diffusive transport it is called. Many a times we say that it is by diffusion. Diffusion means it is basically a molecular diffusion, which is not emphasized, which is not very specifically mentioned. Okay. It is a known fact that diffusive transport is, many a times people say, is to be a molecular diffusion. Okay. And they have used universal velocity profile while deriving this expression, the above expression, the above equation. So, the universal velocity profile has been taken into consideration. Universal velocity profiles are there for a laminar sublayer and for a turbulent core. There are two different velocity profiles are there, and they have made use of these two different velocity profiles to get into or arrive at such analogical expression. Then there is another analogy that is given by the von Karman analogy. What they have done, they have further improved the Prandtl consideration by considering the buffer zone and making use of velocity profile. So, what they have done, improved Prandtl analogy by considering the buffer zone and making use of universal velocity profile. Okay. So, according to this, the stanton is equal to f by 2 and 1 plus 5 root over f by 2 Prandtl minus 1 plus ln 1 plus 5 by 6 into, I am sorry, it is not it's quite long expression. So, we will write like this 1 plus 5 root over of f by 2 into first bracket Prandtl minus 1, then plus ln okay, bracket 1 plus 5 by 6 okay, then Prandtl minus 1 bracket closed, and then another bracket closed, and then this third bracket, second bracket is closed. So, this is the expression that is given by von Karman, and what he has done, as I have told, that he has improved the Prandtl analogy part by incorporating or by considering the buffer zone. As we understand, what is this buffer zone? Buffer zone is basically nothing but the transition between, is the zone where the transition from laminar to turbulent region takes place. Okay. So, there are 3 different velocity expressions which is given, which is also termed as universal velocity profile. So, these 3 velocity profiles for laminar sublayer, for buffer zone, and for turbulent core. These 3 velocity profiles have been taken care of, have been taken into considerations to arrive at this expression. And one thing I should say here, in these 2 standard number expressions, that the f term here, this Fanning's friction factor. So, if somebody wants to put Darcy's friction factor, then f will be replaced by f d by 4. That is very important. If Darcy's friction factor to be used. Okay. So, this is one very important thing that we should understand. So, this way we try to see that what are the different types of analogies and how these analogies are useful for getting heat transfer coefficient values, because already we have discussed some conditions for which the analogy would be very much useful, and also we have seen that this analogy is not only for heat transfer, it also can be useful for mass transfer conditions, and it is advisable to take more accurate analogies, but that may that again depends on the kind of competition and all other things that is needed for doing this, but or what the kind of variations that we obtain when we using Reynolds analogy, or when we will be using Prandtl analogy or von Karman analogy. Also, we can see that when Prandtl tends to 1, when Prandtl is very close to 1 or equal to 1, then all are merging with Reynolds analogy. So, when Prandtl number is equal to 1, there is no point of putting it is automatically switching over towards Reynolds analogy. So, when Prandtl number is very close to 1, then one can always take Reynolds analogy, otherwise they may think of going for the little bit complicated analogy, because there are some more analogies have been discussed. For example, but I am not going in details about that, the various other analogies are Martinelli, then Lyon, then Dissler, etc. These are the names of the different analogies which are available for heat and mass transfer studies. Okay. Now, this is after this we will discuss another important issue which is related to this convective heat transfer or heat transfer studies, that many a times we may find that driving force, that is delta T, is a varying quantity. It may not be a constant one. As we know that Newton's law of cooling says that Q dot is equal to H A into delta T. Now, Q dot is the rate of heat transport, and this rate of heat transfer is dependent on, in case of any convective flow, when there is a heat transfer between two fluids. So, rate of heat transport is very much dependent on H, area, and delta T, driving force. So, H is the heat transfer coefficient that we have seen. There are several coefficients available to find out the values of heat transfer coefficient for different situations, and A is the area. So, depending upon the geometry, we have to find out that geometry, this area can be variable, can be non-variable quantity depending upon the situations that we have to adjudge, and delta T. Delta T is the driving force. At different locations of the flow, this driving force may change. Typical examples for such case we will be discussing here, and to see that what kind of this delta T then you should use. If the delta T is changing for a variable temperature difference, what kind of variables delta T we should use to account for the rate of heat transport. Okay. So, therefore, if we try to see with an example of a double pipe heat exchanger, so what we are discussing now for heat transfer with a variable driving force which is nothing but delta T. So, this is the case we are trying to discuss, and then if you see the case of a double pipe heat exchanger, like say if I draw, okay, and say fine, and something is going out, okay, and so if we plot here also, this is say part A and this is part B, and what we will do is here, so the flow is in this direction say, and here the flow is in this direction. So, what we can see that inside the tube say hot fluid. So, if I say that m dot H and say T H 2, sorry, I will write, otherwise space availability is a problem, m dot H and T H 2, here it will be m dot H and T H 1. Okay. So, this is station 1 and this is station 2, and here it is m dot C and T C 1, and it will be m dot C and T C 2. What does they are this? So, C means cold fluid and H is equal to hot fluid. So, we are saying that cold fluid is passing through the outer tube and hot fluid is passing through the inner pipe. Okay. And this is what is the temperature, okay, and here it is distance with respect to this, and if you see that this will be the variation of temperatures. Okay. So, this will be the variation of the temperature of the cold fluid. So, we can say that T C 1 and the cold fluid outlet temperature T C 2, this will be the hot fluid inlet temperature. Hot fluid also will lose the energy. So, this is T H 1 and this is T H 2. So, we will say that this difference is delta T 1 and this difference we will say as delta T 2. Okay. So, similar kind of arrangement we can see for this is what is called co-current flow. What does it mean? It is also called as parallel flow. In this case, hot fluid and cold fluid are moving in the same direction. So, this is called parallel flow, they are moving in the same direction. This is called parallel flow or co-current flow. Okay. And what is happening is heat is being transported from the hot fluid to cold fluid, that is we know, and the similar kind of situation can happen for say another case when it is a counter flow. So, same diagram we can draw here. like this. So, this is station 1 and this is station 2, okay, and we have the tubes here, okay, and what is happening, it is coming from this side and is going out to this side, and this is like this, say. So, what is happening here? Here also it is m dot c T c 1 and m dot c T c 2, here m dot h T h 2 and m dot h T h 1. So, in this case what is happening, this is called counter current flow, also called or counter flow, or it is called anti-parallel flow. So, what we can see here also, the fluid is flowing, the hot fluid is flowing like through the annular side, through the tube and inner tube, and cold fluid is flowing through the outer tube, and what is happening, but they are flowing in the opposite directions. Okay. And if we try to see the profile here, these are the profiles. So, this is the how it is flowing, and B is saying you the profile. So, this is distance, okay. This is station 1 and this is station 2. What will happen to the profile is like this. So, we can see this is going to happen for this is delta T 2 and this will be T h 2 and this is T c 2 and this is T h 1 and this is T c 1, and this we will call as delta T 1. So, both the cases we can see that along the distance of the heat transport there can be a differences in their driving forces. If you see continuously the T 1 to T 2, this can change, and this variation of the driving force can be linear, can be non-linear, and depending upon the situations. Now, what kind of delta T then we should use when we will be using or getting the expressions for heat transfer coefficient, or when we will be interested to know about the heat transfer rate. That is what is of importance. Now, if we see for the case of parallel flow, if we try to see for differential amount of, say, for the differential area of the double pipe heat exchanger, we know that dA is the differential area, then we know that dq dot, that is the rate of heat transport by this differential area, will be U is the overall heat transfer coefficient into Th minus Tc. So, U is the overall heat transfer coefficient and Th and Tc are local temperatures of hot and cold fluid. Okay. So, that we can see from here, like if I try to say that if you consider a small area, say here, this is a dA, differential area. So, in this region we will assume that the temperature is more or less same, and we say that this is Tc, and in this region here it is a Th. So, this is the temperature of the hot fluid and this is the temperature of the cold fluid. And that way if we try to go, then what we will find is this also can be written as minus m dot h Cph into dTh. So, dTh is the for the differential area, that this is the change in temperature of the hot fluid, and as because the hot fluid is losing the energy, we are writing is minus, because dTh is negative, the minus the dTh is negative, and this negative makes it a positive quantity, and this is equal to m dot c Cpc into dTc. Now, what is m dot c? M dot c is nothing but the cold fluid mass flow rate, and m dot h is equal to hot fluid mass flow rate. Cph and Cpc are the hot fluid and cold fluid specific heats. So, then what we can do is, if we just make use of these two parts, say this is say I say 1, this is 2 and this is 3. So, from 2 and 3 we can write that dth minus Tc, this is dth minus dTc, and that will be equal to dq dot minus dq dot by m dot h Cph minus dq dot by m dot c Cpc. So, this way then we can write it as minus dq dot into 1 by m dot h Cph plus 1 by m dot c Cpc. So, now what we can do again, equations 2 and 3 we can write like that q dot is equal to minus from minus m dot h Cph into Th2 minus Th1, and that is also again equal to m dot c Cpc into Tc2 minus Th1, sorry Tc1. So, this is the for dq dot it is dth, and for if you integrate then it will become Th2 to Th1, and if you integrate here it will be Tc2 to Tc1, and that way then we can write that dth minus Tc by Th minus Tc. From the previous equation and this equation we can write u into 1 by m dot h Cph plus 1 by m dot c Cpc into integral of dA, and from station 1 to 2. So, if we do the integrations then we can find out, this is also from station 1 to station 2, then we can find out that ln delta t 2 by delta T1 will be equal to Th2 minus Th1 minus Tc2 plus Tc1 by q dot, and this is equal to, so we can from here we can write that q dot is equal to UA into Th2 minus Tc2 minus Th1 minus Tc1 by ln delta T2 by delta T1. So, we can write as this one as that q is equal to UA delta T2 minus delta T1 by ln delta T2 by delta T1, which is called as UA delta T Lm. So, this delta T Lm is called log mean temperature difference. So, what we should use when we have a varying driving forces, we should use this log mean temperature differences. Now, what will happen in case of counterflow? In case of counterflow, it is everything remains the same, only the changes is here that everything same, only the changes is that dq dot will be equal to m dot h Cph into dth in place of minus m dot h Cph into dth, because in case of counterflow both the fluids are sorry, here it is dth. Okay. So, this will be the changes. Apart from that everything remains the same, and the expressions also will come out to be same. So, we can do the exercise to find out the values of log mean temperature difference in case of counterflow. Okay. So, this is what, because in this case dth or it is, so q dot is equal to m dot h into Cph into Th2 minus Th1, and here Th2 minus Th1 is also a positive quantity, and therefore, the negative sign is not needed. In the parallel flow there was a negative sign here, but in case of counterflow there is no negative sign needed, because already dth is a positive quantity or Th2 minus Th1 is a positive quantity, but in case of parallel flow it was a negative quantity, therefore, a negative sign was required. So, this way one can do the exercise and again get the similar expression what we get for parallel flow, a similar expression for LMT log mean temperature difference. So, thus we will stop over here, and in the next class we will see that convective heat transfer some theoretical developments in case of convective heat transfer with the help of in the case of a boundary layer flow. We will discuss something on boundary layer flow, boundary layer heat transfer and convective heat transfer coefficient related to the boundary layer flow. Okay. Thank you very much.